From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to those stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
Yeah, well, a couple months prior, we just founded Impressio. And so it was just Amir and I in a very small office, sharing it. And we saw this invitation to say, hey, there's this first and future competition. And there's also some grant funding, research funding to develop new technologies for helmet protection and increased player safety. And so we were lucky enough, we got really kicked off in this. So we were invited to do this pitch. It was like a Shark Tank style pitch. It was in Minneapolis for Super Bowl 52. It was Eagles versus the Pats. Yeah, it was a great game. And I won't say who I was rooting for. Okay, even though I grew up in Pennsylvania, I don't know if I had a dog in that fight. But so we went out. We kind of pitched the technology, and it was really nice because they gave us the oversized check. I felt like we were, season one of Silicon Valley. Got this, oversized $50,000 check. It really helped jumpstart our, investigation or journey into helmet safety.
That was ChrisYakacki. Chris is an associate professor at the University of Colorado, Denver in the Department of Mechanical Engineering. He also serves as president and CTO of Impressio, Inc., a startup company focused on commercializing liquid crystal elastomer technology, which was spun out of and licensed from the university. From an academic standpoint, his goal is to develop a world-class research group as part of the Smart Materials and Biomechanics Lab. One theme of the SMAB Lab is to focus on the development and application of multifunctional smart materials with an emphasis on biomedical devices. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher. Hey, Chris, welcome to the show. Excited to have the conversation today. There's going to be a lot to cover. I think we'll get into some of the work you're doing in sports, some of the work you're doing in materials. So right up my alley in terms of two things I love. But as we get started here and kind of get into the conversation, do you want to just start with a little bit of background, kind of like maybe just start way at the beginning, like where you're from, like what got you interested in kind of the engineering track and what you're doing now?
Oh, wow. I mean, if you start from the very beginning, I grew up in Pennsylvania, York, Pennsylvania, like science and math, but I decided to go into engineering for those reasons. Found University of Colorado at Boulder, loved it, had a great undergrad, didn't want to get a job, so stuck around for graduate school. I think that's what I would say a lot of graduate researchers did, but I stuck around. Along the way in graduate school, I did find a pretty interesting path. I got into, smart materials, smart polymers. At the time, it was shape memory, so materials that could change their shape in response to some stimulus. And started a company with my advisor and a few other folks. It was a company, MedShape, and we were looking to use these shape memory materials, both polymers and alloys, for orthopedic devices. And so at a grad school, it was kind of nice. Kind of had my own job lined up for me. I was lucky enough to win a few SBIR grants to help pay my salary. Was there for 5 years in Atlanta, working for MedShape. And then I would say somewhere around 2011, decided I might want to do the faculty track. Don't ask me why. I think you need to have a few screws loose to become a faculty member. But was lucky enough to return to Colorado, University of Colorado, Denver, in which I kind of switched fields a little bit, still in the smart materials, smart polymer space. But this time I was looking at liquid crystal elastomers. And these materials, I first got interested because they look like artificial muscles when heated and cooled, or maybe you would shine light on them or expose them to some environmental stimuli. They could, I'd say, either contract or extend, or they would have this repeated actuation in the material built in. And then we found out that these materials do more than just, I'd say, move and change their shape, but they're also really effective energy dissipators. And so just when you pull on them, they feel like silly putty, but they don't break into two. Eventually they have an elastic limit. And so there's highly viscous, highly rate dependent, and they can be highly anisotropic as well. And so the interesting thing about that is, within that polymer, we can make it directionally dependent. So in one direction, it could be more stiff, less compliant, and another one, have enhanced dissipation. To me, that got me really excited because at first I was thinking artificial muscles. These things could, contract and extend repeatedly. But then I was thinking, what about artificial, like cartilage tissue? Someone keeps calling it something like artificial tissues. And so we kind of looked at how do we take this material and kind of how do I introduce that into new commercially realizable devices? And so I started another company, Impressio, and kind of our mission is try to take this liquid crystal elastomer technology into the marketplace. And how to do that can be tricky, and I'm sure we'll talk about that. But we have applications in orthopedics, we have applications in sports, in the military, and we're looking at a few other areas. I don't know if I can touch on all the areas we're looking at, but anywhere where you might want to dissipate energy. And energy can come in all shapes and sizes, or forms, I should say. Maybe not sizes, but whether it be vibration, whether it be impacts, whether it be I think I can say thermal, whether it be acoustics. Dissipate energy and or mimic human tissues. That's where I get really excited, trying to introduce this class of materials to the world. I think that was hopefully professors can talk forever, so hopefully that was a very short background of me and how I got to where I'm at today.
It's a good background if it leads to more questions, which I've got several.
So, perfect.
So when you were in grad school, kind of, and starting up with, I mean, you're in the middle of doing research, you're writing papers. Like, how did you find the time to do the startup, or like what was the conversation like in terms of getting your first kind of venture off the ground?
Well, my dean, Marty Dunn, has a great saying: if there's not enough hours in the day, use the night. Okay. And so I think I've given up nights and weekends for a long time. I'd say most Sundays, and I'm working, but that's how I find the time. Just kind of make it up. What was the second part of that question? How did we maybe get that off the ground?
Yeah. And kind of what was like your drive to do the entrepreneurship path? I mean, it's not super common in the kind of, especially in the graduate school academic track, to kind of be close to industry and doing a lot of the stuff other than research. So was there anything that, like, hey, you always wanted to start a company or be part of the startup kind of ecosystem environment?
Yeah, no, it's a great question. And to me, it's a little paradoxical because a lot of faculty or researchers tend to have good introverted traits, right? Where you can buckle down and really dive into the literature, right? Or just, spend an entire day reading up work or in the laboratory alone. And so you can have this very introverted nature and to be kind of isolated, if you will. But then at the same time, I would say people who are drawn into research and even just academia don't like to be told what to do. They want to lead their own path, right? Now, that's one of the cool attractions of being a professor is I get to pick what I work on, right? There's no one telling me I have to research liquid crystal elastomers. And so in that regard, when you think of researchers, you get to pick what you study. You get to pick what you want to dedicate your time towards and be kind of meaningful, impactful. And from that regard, you're very kind of close to being an entrepreneur. You're not being told what to do. You're trying to say, hey, I want to always push the bounds and do something that's, I'd say, novel. That's not just the same. I mean, in publishing a paper, you can't just say, hey, 3 other people have shown this works. You need to say, hey, we're the first to show, right? We've advanced the field in these ways. And entrepreneurship to me is the same way. Is you say, hey, we have a new idea for a product, right? A new technology, and we want to be the first to demonstrate that it actually it's worth something, right? It's meaningful. It has value. I guess I'll probably talk about value. It's a bunch more today. And that's tricky, right? Because in academia, sometimes it's about what journals you publish in. And that might be your validation. I made it in Advanced Materials or Nature or something. And that's great. Like I did it. I'm validated that my idea was good. And entrepreneurship's a lot different. Like I really don't care if you publish. But I think it stems from a lot of researchers wanting to do their own thing, pick their own meaningful projects. And to me, entrepreneurship is very similar to that. It's going to be time intensive. It's going to be a million questions. There's no one going to tell you the exact way to do it. But yeah, you're just trying to push the boundaries and do something new.
And there's a lot of unknowns. I mean, even like, let's take the example of the liquid crystal elastomers, right? So can you when you're kind of working on that space early on, I'm always curious about kind of like the origins of where that kind of technology came from. Was it something like, hey, like we've found in the lab that we can kind of make this stuff, or it's adjacent to another material that we've seen, or shape memory or something like, hey, could we do it with elastomers? Or is it more like, hey, like look at the way the body moves, or a knee joint or something. Like there's multiple materials that have directionality that are soft and hard. Like the body is a good example of like all these different kind of meta materials. So like, was it a mix of like how that came together to push the field of liquid crystal elastomers forward? Or was it like, hey, like I got this idea, it needs to happen?
I would love to say it was carefully crafted and it was well thought out. And I always joke with my students after the fact, like as expected, this was the plan all along. And I'd love to be able to say, oh yeah, there's this huge need, for biomimicry, and we kind of discovered this new way. No, it was more of a stumbling into it. I mean, just to be perfectly honest, I knew I liked materials that were unique, that could do, have behaviors that just aren't common, that aren't commodity. And in the liquid crystal elastomer, realm, a little different from the liquid crystals, but when you bind it into a polymer, it had been around. Like the science had been around. They were kind of first predicted in the late 70s. And there's a nice little joke in polymers, is that when you invent a new polymer, you're probably going to die before you make any money off it. And so it's kind of been, historically, it takes a while. So I guess the good thing is, I was born in the 80s, so it had time to cultivate and build a little bit of this base to the technology before I came along. By no means did I invent liquid crystal elastomers, but the materials had just been really hard to make, right? And so like synthesizing them was just really a pain, just a long story, a pain in the butt. And so I think my contribution to the field was always as a mechanical engineer. I'm not a chemist. Actually, I would say I'm okay in the lab, but I think any of my students or people that work in the lab would say, get out of the lab now to me. I found my skills have dropped considerably. No, but my contribution was how do you make it accessible to folks in a lab that don't need an extensive background in polymer chemistry or synthesis, and to make these materials and be able to manipulate them and turn those into devices. And so I guess it was kind of good for me because, the field had been around. There was at least literature showing that it had, I'd say, interesting dissipation characteristics. It had this kind of actuation characteristics. It can be anisotropic. And so it was kind of nice that some of the groundwork was laid there, but the barrier was just, I was always told, you're a mechanical engineer. Good luck making them right now, because that was kind of the consensus when I was telling people, yeah, I'm going to work at CU Denver. I'm going to try to start looking at the liquid crystal elastomers. It's just fascinating materials. Good luck. And I was like, that's not the greatest words of encouragement, but we kind of overcome those challenges. And it was just really just along the way, since I had that background in orthopedic devices with MedShape. I was looking at some of my projects were soft tissue, either fixation or reconstruction, whether it be like a rotator cuff tear, an ACL tear. So kind of looking at soft tissues quite a bit. And so that was always kind of in my mind. People tend to stay a little bit in their comfort bubble. So for me, orthopedics was my bubble. And looking at that material, it didn't take too long to be like, this thing really behaves, not the actuation part was cool. And I'll be kind of blunt with this. I like to make fun of academics only because I'm an academic. The actuation's cool. You get great papers out of it, right? You get wonderful visuals and photographs. But that's sometimes hard to do, especially like changing temperatures 40 degrees and doing that quickly. And if you're going to do that in the body, there's no way it's going to do it. But it had this passive mechanism of saying, hey, I can be this really soft shock absorber. And the more I looked at it, the more I was like, kind of resembles either cartilage or the disc in your back. And I started putting the pieces together, I say slowly, started thinking, hey, this could actually be a really good fit. But yeah, I really wish I could say, oh yeah, I planned this out. It was just a master plan that's come to fruition. Not so much.
How do you actually make them? Or like, what's the delivery mechanism to like, there's like a handful of ways to manipulate polymers, right? You can injection mold it. You can kind of compression mold and 3D print and like extrude it. What's the mechanism, or like what's the raw form of these materials? Is it like a two-phase thing? Is it kind of like a thermoset, or more kind of thermoplastic type of material?
It's a great question, and I'll try to answer it as succinctly as possible. I'd say a couple of years ago, the answer would have been real simple. It'd be mostly, I'd say, casting and molding techniques, and it's a thermoset. Even though you could do some fancy, I'll say, dynamic bonding, in which case some people say, is it really a thermoset now? But ignoring that part, a couple of years I would say, hey, we can mold these into any chemistry, whether it be really thin films, or kind of say bulk parts. Just think of something. Just think like a big, I don't know, like one of our demos was the lacrosse ball, the LCE lacrosse ball. It was a rubber that didn't bounce, so it was kind of sad when you dropped it. But in additive manufacturing is an area that you know and love. It has been progressing and advancing quite a bit. So now we're kind of in this spot where we can do it with just a variety of techniques. We can make this material into foams. We can 3D print this material using like direct ink writing or DLP SLA techniques. And we've even electrospun this material now. So again, kind of my contribution was, how do I make it easy to make, right? How can we be makers, if you will? And so I think that was my contribution to the field, and that's where Impressio really comes in with our, I'd say, skill set and expertise. Is we don't want this material to be just pigeonholed or just limited to one single application or one form. We try to spend a lot of time marketing or figuring out, determining what different markets we can put this material in, and how might we manufacture it for those markets. So sometimes it might be really thin sheet form. Sometimes it might be a 3D printed custom device of just the material. Sometimes we just need to cast a bunch of parts. Let's say for our helmet technology, we're casting a lot of, they look like pillars. They look like cylindrical pillars that absorb energy when impacted. And so it kind of just depends on it, but we're in a pretty interesting spot where manufacturing is, we want to be as flexible as possible to meet kind of really any application that comes up.
And so with Impressio, is it more of like, it's fundamentally a materials company, but you're making the material in some sense, but you're also figuring out applications or maybe partnering with companies that may have a need or trying to search for companies or applications? Correct. Is that kind of how it works?
Yeah. And this is, I say the challenge. You're right. The challenge, if you want to start a company that is more of a material technology, a platform technology that you would like to license out, the trick that still was different than biomedical devices was, a biomedical device is very simple. Hey, what are you making? Like, oh, I'm making a suture anchor, and everyone can see the suture anchor and they can put their hands on it. And people understand, okay, you need to manufacture it, sell it to doctors, get simple. That's how you make your money. It's a very clear path. Being kind of where we're at, I wanted to kind of be a little bit up the supply chain, if you will. Like let's supply material that could go into all those cool devices out there. The hard part about that is no one wants to be the first, right? Not to say that. No one wants to say, hey, why don't we, as a manufacturer, let's bet on this new material technology that historically has been limited to just laboratories. And I'd say geeks like myself in the lab, I'll say that's been historically difficult to make, that there's not a lot of data on. It's hard to convince someone to say, hey, you want to try it. And if we haven't had, we wouldn't have much success if we just sat back and said, if we build it or if we make it, they will come, right? The good old Kevin Costner line. But so we've kind of taken this role to say, well, we need to kind of be a little bit of experts in some of these fields that we're targeting. So like helmets, for example, God, we spent the last, since probably 2018, studying what actually makes a good helmet. What is the limiting factor between, I'd say, just traditional foams in these materials that we could replace? And because if we just go to a helmet manufacturer and say, hey, we have this great material, they won't know how to use it because it hasn't been used before, right? If we gave them a new foam, I'll pick on foams, just for example, they're very familiar with it. So they would understand exactly how to test it, how to manufacture it, how it would insert into the helmet. But for us, we kind of want to kind of break away, say this is just fundamentally different. It's especially maybe if we're doing with the directionality, like all of a sudden now you can have a polymer that it kind of has this alignment, just like cartilage and your not cartilage, collagen in your cartilage. Right? It has this alignment, so now the properties in one direction will be different. Yeah, I don't know if they've ever made something like that before. So, and then when we start talking about liquid crystals and all the states they can be in the processing, they kind of, manufacturers kind of want to see some demonstration proof of concept. So we try to become a little bit understanding and experts into the application for going after. And then it makes it tricky because how do we select which ones we want to go after? Like we can't do everything. Like, so we try to pick a few markets that are either high visibility, high value, or combination of the two. So, it's been tricky. Yeah.
In that, I've had similar projects along those lines. And one of the challenges we always face is that finding the right person within an organization that understands enough of how the product is made, as well as the challenges, that is also open-minded to new materials or new some sort of manufacturing processes. Super time consuming. Like it just takes forever within most organizations, because I struggle, like it's a little bit of lack of creativity, or like just showing you need to really show the path of how it could get to one place from just a block of material on the desk to a finished product.
Yeah, path. Oh, and then I think I said this earlier, path and value, right? Why can't you use, like for us, we'll always face, not always, but we'll often face why can't I just use like silicone, right? It's an elastomer. Isn't that energy absorbing? Isn't that soft? And so kind of, explaining that, yeah, it's not fundamentally like anything else. This is how it could work. And this is what would build that value compared to what you have right now. So I say value propositions and how you might realize that is tricky. I guess one thing when you say, how do you find the right people? I guess I was lucky enough. I'll give a plug to this program, National Science Foundation. I got to thank them. They've given me lots of grant money. Thank you, NSF. But they introduced the program in their IIP, Innovation and Industry Partnerships, a few years back, called the I-Core. And I always like to call it like your mini business boot camp. It was 6 weeks of a butt kicking, I'll say that, where you had to interview 100 customers in a specific segment. So I think we went in, me and my co-founder Amir Torbadi, we went in and we had this idea that maybe we should use this for knee replacements, right? And you don't need to have your final idea done, but they want you to go in with some technology and an idea. Just, hey, what do you think this could go into? And then you spend 6 weeks kind of proving, maybe is this a good idea or not, right? And it was rough because, in 6 weeks, I know you interview a lot of folks, but, packing in 100 interviews in 6 weeks is really time consuming. And of course, I was an idiot to do it while I was teaching 2 classes. And it was a terrible idea to do it, mid-semester. But it really kind of taught you how to find the right person to talk to, right? Maybe hopefully I didn't say that wrong. Sorry. I had a brain fart. It's early in the morning. Help identify who is that right person in the organization, or how do you get to them, quickly. So, and it gets you out of your bubble. Again, like I said, there's that introverted, research bubble where you're like, oh, I know the answer. I have a great idea, but really saying, okay, get out of your lab. And I think they harped on this, get out of the building. It's what they harped on quite a bit. But get out and go talk to some folks and actually find out if your idea has any merit or can people be interested. But that's how we kind of learned, kind of cut our teeth and got trained up on figuring out value and figuring out the right people to talk to.
And I imagine too, on that same front, is like, because it's such a new material, and I think you hinted at this a little bit, is that kind of the standard testing that you would do, or that people are used to seeing, like, may not apply, or like they may require something different. So at the same time, you're figuring out, okay, like, how do we communicate the story in a way that seems credible and has, whether it's standards or some testing behind it. So can you talk a little bit about, like, how do you know that this is a good material, or like, what are the things that people are looking for, or that you want to show? Is it kind of thermal resistance? Is it impact strength? Is it kind of rebound or kind of dissipation of energy? Like, what are some of the actual tests that you're doing in terms of kind of shaping the material, or trying to create that story so that when you go to a certain market segment, you say, hey, like, we can reduce impact outcomes in X, Y, and Z? Like, are there certain things that, like, people are asking about, or that you're trying to communicate?
I wish I had a really simple script. Like, oh, we just run this one test and it's done. And some people try to do that. So if I look at let's say data sheets for 3D printed elastomers, obviously that's an area that we look into quite a bit. Who's publishing? What's published on what data sheet, right? From current industry players in 3D printed elastomers. And maybe one common one, we'll see some common things like, what's the tensile strength, right? What's the tear strength? One could be maybe, what's the resilience? And we got, I love this little machine we just bought, it has this little mass and it bounces on the sample, and you measure out how high it rebounds, right? And the problem is that that's just such a limited part of the story, especially when we're talking helmets, because even like there's so many variables, like even with the foam, you got to then say, well, what's the foam's density, right? And then, well, how big of the foam were you testing? And what did you drop on it? Was it something that was a little sharper, or was it something that was like a flat, more like a flat anvil, or a flat impact head? And did you have a layer on top of it, right? So and we've noticed, and I'm picking on like impact type applications, is that when we talk to manufacturers from, whether it be bicycle to hockey to football to military, they all have very similar tests, but they're all slightly different, right? And so it's really hard to go in and just say, oh, we had this, really great impact thing. Because then they'll say, well, how big was the sample? What was the overall apparent density? What were the conditions that it was tested at? Like, what was the height that you dropped your mass from, or what was the speed that it impacted? And you could say, well, couldn't you normalize that by energy? But even that's tricky because, if it's a drop from a lower weight but heavier, or drop from a higher weight but lighter, maybe the energy could be. There's so many variables in telling that story. It's hard to craft that. So I'm going, as my physics teacher would say, I'm going to Boston by way of China, but it's very there's a ton of variables, and that's one of our challenges to try to do. So we're trying to right now work on some, I'll say, data sheets that can give you that really quick look, and then also try to compare it to competitive materials under, let's say, conditions that would be interesting for a given application. But it can be tricky. So in orthopedics, we're going to do a lot of wear testing. But for a helmet manufacturer, they probably would not care about wear testing. That's not one of their big things. So that's me dodging the question, saying a lot, and then really the answer is it depends, and there's just a ton of variables. Which I said that's the tricky part with some new materials. I think it was just a device I could say, let me compare to a competitor, and here's our results. But it's sometimes not that simple.
And maybe grounding the conversation a little bit in terms of kind of a single product that you guys are working on. Can you share a little bit about the helmet challenge, and what was it, or what kind of is the challenge, and what are some of the things you guys are doing as part of that?
Yeah. And so the NFL helmet challenge, and it's kind of part of a big, broad, I'd say, head health tech initiative, has been really great to us. So, I have to say that. I don't have to say it, but I will say it.
Roger appreciates
so
it.
That, yeah. And so back in 2018, so February 2018-ish, we had just, a couple months prior, we had just founded Impressio. And so we're, it was just Amir and I in a very small office, sharing it. And we saw this invitation to say, hey, there's this first and future competition. And there's also some I say, grant funding, research funding to develop new technologies for helmet protection, and increased player safety. And so we were lucky enough, we got really kicked off in this. So we were invited to do this pitch. It was like a Shark Tank style pitch. It was in Minneapolis for Super Bowl 52. It was Eagles versus the Pats. Yeah, it was a great game. And I won't say who I was rooting for. Okay, even though I grew up in Pennsylvania, I don't know if I had a dog in that fight. But so we went out. We kind of pitched the technology, and it was really nice because they gave us the oversized check. I felt like we were, season one of Silicon Valley. Got this, oversized $50,000 check. But really helped jumpstart our, I say, investigation or journey into helmet safety. And then we were lucky enough to get some more kind of funding on top of that through their head health initiatives, and then to develop our material, because there was a lot to learn. And so I don't think anyone. I mean, I always applaud people who want to go in and try to disrupt the market and shake things up, because that's kind of what I want to do. But that can be tricky too, because we have to learn all about helmet safety and all the protocols and what goes into it, and understand how they make the decisions to either design a helmet or to pass a helmet, whether it be from like a standardized test or not. But about a year or so ago, in Youngstown, they decided, hey, we've been funding a lot of teams. We've been, kind of really promoting new technologies to increase player safety. Why don't we make a big event out of it? And it was kind of exciting, right? So you could apply for some money, and you get a year to submit a prototype, and you got to hit the very high or a high bar. So it's actually a low score. It's kind of one of those like golf scoring. They set a very high bar, but it's to achieve this very low score to basically create the safest helmet ever designed, and not just by a little bit, not just like, oh, well, it's really hard to describe how this metric is, but not just, hey, we're 5% better, but I kind of like to say it's more like 20 to 30% better, right? And that's maybe that number. Don't hold me to that number as an exact, but a significant leap. And so for us, our approach in our team over the last year was, hey, how do we kind of marry our material, being this liquid crystal material, into a helmet design and do it in a very efficient way that we can test, we can iterate, prototype, and it's probably not a surprise to your listeners. We decided, hey, combining it with additive manufacturing might be the best way to go. And so and this is something it's fairly, I would say fairly common, but it's been generating a lot of buzz. I know there's 3D printed helmet designs out there. Some are concepts, some are on the market. We wanted to use 3D printing as an interesting delivery mechanism for our material. And so kind of the way we approached the challenge was we can 3D print, I'd say, this liner component that could conform to your head, that can be tailored kind of in each specific region very, very finely. And then at the same time, add our material to it, use that lattice or that structure as a kind of holding mechanism or delivery mechanism to hold I'll say a pillar. That's why I said like this pillar of our material. And so it's kind of a little bit of a composite. In one aspect, it's a 3D printed liner, structure, lattice foam, however you want to call that. And then we could insert our material into it. We wouldn't need to make the entire helmet and the entire internals out of our material. It would probably be prohibitively expensive, but this way we could kind of realize designs, iterate just super fast. And so we spent the last year doing that. We got this EOS P770 machine and cranked out. I don't know if I have an exact number. I know in one test location we did over 1,000 tests. I have boxes and boxes and tables of 3D printed liner components. I'm trying to pawn them off on my students. I'm teaching AM now. I'm like, hey, who wants some SLS parts? And I was hoping they would steal them on, and they haven't. So now I got to figure out what I want to do with the old reject designs. But so we submitted our prototype. The prototypes were due about a month ago. Maybe it was a little over a month ago. I lose track of time. And I can't really say what the results are. I kind of have some insider information, but by the time this releases, I'm sure that the challenge results will be out. But I can say it was very hard. It was a very hard experience, but at the same time, it was pretty rewarding, and we're happy. We're very happy with what we designed and how we performed. So when I say that, we tested in our lab, we tested in some collaborators' labs as well. I think we designed, again, the safest helmet ever out there. Getting it to be commercialized, that's going to be, that's problem number 2, right? Proving that your concept and your design works. That's the step 1. Getting it to the market, step 2, and that's what we're trying to figure out now. But I think I can leave it at that. Let me know if I answered everything you wanted there.
Yeah. So just digging into that a little bit. So you would you'd use the SLS process, which is a powder process was it with nylon or with another elastomer to print the liner?
Yeah. So, well, nylon would be good if it was a single impact. Don't really, in that case, right. If it was a single impact hit, nylon would do wonderful. But we were looking at 3D printed elastomers. So, okay. And this is kind of I said my area has been kind of elastomers as of late. So on the EOS side, we were using a TPE 300, but then we also have our elastomer, and we did our elastomer both cast and 3D printed, and we did 3D printing on I'll just say some desktop type SLA and DLP machines, but we kind of been surveying the whole landscape of 3D printed elastomers, and so. They're tricky. Elastomers are tricky. I mean, making liquid crystal elastomers was hard enough. 3D printing, even just general elastomers are hard. But yeah.
Would there ever be a potential to put your liquid crystal elastomer into a powder, or is it more like a resin style material?
I know your research was back on SLS, so we have thought about that. If we could do a little. I think you did some cryo grinding back in the day, and then did some experimental materials on like a P1 or something. We haven't done it yet. I don't think not to say it can't be done. Sure. It's just I think we've got actually really excellent results from both direct ink writing and some of the SLA type stuff. So we haven't had that need yet, but it could probably be done. It's funny, again, a couple of years ago, if you said, "Can you 3D print your material?" I'm like, it's this far away, and now we're just doing it. Regularly. So
that's great. And so maybe shifting gears a little bit from kind of the Impressio side, can you talk about how 3D printing comes into your kind of day-to-day work at the university, and I mean, you mentioned some of your students kind of are working on 3D printing. Like, how does that kind of play into your research, your academic teaching, and things like that?
Yeah, and I've kind of going back to like, how do you find the time, right? When you say, how do you find the time to, be a researcher and start up a company? I think one of the tricks that I learned from my advisor, a guy, Ken Gall, is to really kind of align some of these efforts, right? And so, if I'm interested in, I say, 3D printing on one hand, don't go do something in, I would say, injection molding on the other, right? Try to align some of these efforts. So it kind of keeps you going along at least a track, the way I'll say it that way. It was kind of nice in the sense that, my students actually really helped push me to get into it. I got to give my students some credit in the sense that I had a good crop of students. I think pretty much all of them have gone now, but I wasn't even really thinking the 3D printing again about, you say, maybe like 4 or 5 years ago. And we got a new dean, Marty comes in, and he was very big on additive manufacturing. He was coming from Singapore University of Tech and Design. He's like, hey, kind of opened my eyes to it, invited me out to Singapore. I got to see their facilities. Wow, that's really cool. On the other end, I had all these students like saying, hey, can we buy these printers for the lab? And they're kind of tinkering, building their own. And so I kind of got pushed from both sides to do it. And so I kind of got excited about it. I said, well, hey, I don't want to be maybe teaching the same old classes. Why don't I develop a class on additive? And then that helps, what I'm doing in my research. And then that kind of helps what I kind of know where the industry is heading or trending. Using Impressio, I can see what are some of the, what are the challenges that we're facing, and then how can I bring that into the classroom and try to at least give some of those experiences to the students. And I always love it in the beginning of teaching AM is, I ask like, hey, when should you do 3D printing? When shouldn't you do 3D printing? Like, what are the limitations? And I love that first week's answers because they're just all over the map. And, there's still that common misconception about prototyping and materials aren't strong. And you could never, actually do anything beyond just, trinkets with it. But bring in that experience from, no, this is what the industry said. This is, companies we're working with, right? And so, yeah, using kind of all my, I'll say, startup experience, using some of our industry collaborations, and just trying to tie it all together and at least have it going down a singular kind of, not singular, but along a single direction and not be too orthogonal to each other.
Yeah, and I'm sure it's combining a lot of your kind of expertise and skill set where like you've got this materials company that you're working on, but then as a mechanical engineer, you have to think about mechanical systems and for sure design as well, like how you're designing for additive processes this entire time, even going back to the helmet, right? Like you can put in lattice, you can put in different structures, your multi-material composite system. So like there's a lot going on there in that world.
Yeah. And on top of that, I always, if I got like super fundamental thing I like about, say 3D, I'll go to the direct ink writing. In our material systems, it's cool because I can control chain alignment, which I think is you could say it's nanoscaling. I think most people would agree with that. I can control liquid crystal alignment, which is more of a mesoscale, more on that micron area. And then with the 3D printer, I can control like a lattice structure that's more of a micro macro scale. And so, I mean, even from that, just even within the material and the process, I can control 3 different length scales, which I'm like, that's cool. And then how do I integrate that into a system, right? So.
Yeah.
A lot to be done.
And so you built this really cool career in the space, kind of combining entrepreneurship, academic, kind of research. I mean, you deal with students on a day in and day out basis at undergrad and graduate level. Like what, as you see the additive manufacturing industry evolve and kind of some of the companies popping up in kind of the Denver, Colorado area, which is huge in aerospace and things like that. Like what advice or like what skill sets do you kind of try to teach or instill or kind of help students kind of curate as they're kind of starting their career and building into kind of maybe working in a job in additive manufacturing or trying to find a company or maybe start their own?
Yeah, and it kind of goes back. I think I said earlier, probably talk about value. Right? How do we talk about value? I can give a shout out to So the John Hart, when I was on sabbatical, I did, most professors go on sabbatical and have a great time. I was taking online courses, and I took took John's additive manufacturing course, and I love value at scale, right? Is one of the things he promotes and harps on. And I want students to come around, not just knowing how to 3D print, because I don't want them to be, and this isn't bad. I don't want my engineering students to come out and only just run a 3D printer. I want them to make a business case to their management, why they should be either purchasing one or switching. And then also identifying when they shouldn't be, 3D printing. So I think that's like my biggest goal. I mean, I love to teach them new skills. The printing, I would say it sells itself. It's exciting enough. And I have to thank really all the manufacturers who make printers, put out these wonderful promotional videos that talk about how they work. I'm like, oh man, you're doing my job for me. This is wonderful. But I say teaching how the printer works, that's kind of easy. I like to marry it with doing some design work. Engineers should be doing design. I'm a big fan. I'll give a shout out to Entopology. They were kind of one of our partners for the helmet challenge, but how to use that software, because I also teach, sometimes I'll teach our intro to CAD and SolidWorks course. And, that's your boundary representation files. That's, your CAD files. I want to say you can't do optimizations and crazy lattice structures and generative design in CAD programs, but I really like the Entopology platform to doing it. I just find that I can be a lot more creative with it. So I want to teach them those skills. So when they go out and have an interview, they have a portfolio of designs that hopefully an employer is like, how the heck did you design that? Like that's kind of the response I would love. I would love that to happen. And then also they could at least come up with somewhat of a business case to say, hey, this is how we'd print it, and this is why it would make us some money, right? Like this is why it's actually better than us either going to injection molding or machining. And there's nothing wrong with those techniques. There's a time and a place, but I want them to just be able to be credible, because again, we're not all our students aren't going and working for, I'm trying to think of a company that exclusively 3D prints, working for Desktop Metals. I had a student, Nick. Nick's my PhD student. I won't say his last name, not to embarrass him, but he's working at Desktop Metals now. They can't all go and do that, right? And so, if you're working for maybe a local company that's thinking about adopting it, I want our engineers to be able to then make that business case, because that'll make them more successful engineers, and hopefully help the industry as a whole too.
For sure. Well, I appreciate you sharing your story today. This podcast will drop around the same time that the helmet challenge results come out. So fingers crossed for you. We're excited to see the results there, and we'll talk to you soon, hopefully in person one of these days.
Great. Yeah. Hope to see you soon, man.
All right. Thanks.